Could you comment, Chris, just where you see the future of semiconductor manufacturing headed in the next 5 to 10 years? This is obviously an extremely tenuous time now. 5 years down the line, most politicians anticipate there's going to be some significant event with China, with Taiwan. What is America's response? What is the global response, especially considering how disjointed each aspect of the semiconductor manufacturing is, as you illustrate in the book?
You see right now every major government in the world, US, Japan, Europe, Korea, Singapore, India, they're all pouring money into increasing support for chip making in their countries. So we're going to have an impact from all of these incentive programs on where chips are manufactured, but the impact will be less dramatic than I think it might at first seem, because the capacity that's been built up over the last several decades is enormous, and we're not going to shut down existing capacity. So we'll be changing on the margin where new plants are built, but that's not going to, that will only slowly impact where actually the capacity is located. And so in 5 years' time, I think we should expect, under current trends, that most advanced chips will still be made in Taiwan, which is not what most of us would like to hear. That's not the outcome that is ideal from a security perspective, but I think that's the reality in which we're operating.
And can you comment on why that is, Chris? I mean, it seems like there's a very concerted effort to bring chip manufacturing to the United States. And that's an interesting perspective that's still going to be largely Taiwanese dominant. Why? What is missing? What needs to happen in order for that to not be the case? And then why do you feel that will still be the case?
So if you focus on processor chips, and we can differentiate different types of chips, but take processors to start. There are 3 companies in the world capable of producing anything close to cutting edge processors: TSMC, Samsung, and Intel. Intel right now is a couple generations behind TSMC and Samsung. So we could debate whether you should really categorize them as the most cutting edge or a bit behind. For Samsung and TSMC, they're going to invest some in new facilities in the US, but most of their capacity will remain abroad. So TSMC, under current plans, is going to have 600,000 wafers per year produced in Arizona. By contrast, current capacity in Taiwan is well over 10 million wafers per year. So we're talking less than 10% of production in Arizona. Samsung, it'll probably be slightly more as a share of its overall production in the US relative to Korea, but it's not going to be a majority under current trends. And it takes so long to build chip making facilities, 2-3 years, that we already know what the situation is going to look like in 2026. And 5 years away is 2028. So unless there's massive investments next year, the 2028 picture is going to be clear by end of next year. And under any of these scenarios, we're going to see shifts in investment, but shifts in overall capacity in terms of its location can only happen over periods measured in years or decades.
Chris, beyond the physical buildings, is there anything that limits the ability to port the best-in-class TSMC manufacturing capabilities, supply chain, human capital, intellectual properties, or is it really just that they're only building 10% of the facilities in the US?
Well, it's the facilities, it's also the machine tools, which are produced by a small number of companies. Capacity is limited. Many of these companies book out their machine tools 12 months in advance, 18 months in advance, depending on market conditions. And it's the workforce as well. The workforce is really where the special sauce of these companies lies. The workers are limited in quantity. They're trained over years or decades. And it's not so easy to say, let's double the workforce and move half of them to Arizona. That simply can't be done overnight. It can be done over a long time. And it's beginning to be done, but it's not something that can happen immediately.
And one of the interesting things you talk about in the book as well, Chris, is Moore's law functionally ending, right? There's this observation that computer chips have basically both halved in size, but also doubled in processing power functionally every year since their invention. And we are getting to the point where the physical infrastructure is completely limited, and it's just only so small that you can create any object in order to get this done. And what are the implications of that when it comes to your outlook on technology, the competitiveness of the semiconductor industry? And if I could add on one more question on the 3 that I've already sort of asked there, what areas are you excited about in the future, specifically from a US investment perspective?
So when Gordon Moore first set out the idea behind Moore's law in 1965, he actually had 2 provisions in the law. The first provision was that you get a doubling of processing power every year or 2. That's the one we remember. The second provision was that the average cost per transistor would decline over time. In other words, you get a free lunch of computing power by shrinking the size of transistors and packing more of them on chips. That second part of Moore's law stopped working around 2015 when we transitioned from simple transistors to what's called FinFET, so 3D transistors. It stopped being cheaper to produce them. And so we're no longer getting that free lunch anymore for the first time in half a century. We're still getting the increases in processing power for now. We're still shrinking transistors and stacking them on top of each other now. And that will last at least for the next 5-7 years, harder to say beyond that. But there's no doubt that we are relying more on other techniques to get functional improvements in computing capabilities. One is new architectures. The best example of this is the GPU, which is now the type of chip that's training most AI systems. GPUs are an entirely new way of designing a chip. Actually, initially for computer graphics, now used in data centers. And had it not been for this architectural innovation, we'd be far behind in terms of our ability to train AI systems. Second is packaging, which for a long time was the least interesting part of the chip industry. You made a chip, you put it in a ceramic package or a plastic package, glued it in there and shipped it off. There was no R&D, no value add. That's changing a lot because right now, one of the key challenges is transferring data between chips rapidly. And so if you can package chips by putting them on top of each other, for example, or right next to each other, you can limit the interference as data is pushed back and forth, limit the distance the data has to travel. You can also package different types of capabilities next to each other. So optical interfaces, for example, or different types of sensors right next to chips. And so there's a ton of innovation in packaging right now. And when we look at the future of innovation in the chip industry, we're going to get shrinkage of transistors for at least the next decade. We're not going to get the cost declines that were associated with them, but a lot of the performance improvements will come from either new architectures or new packaging technology.